Morning everyone. So today we're just going to finish off a little bit with the solar panel stuff we introduced yesterday. We're going to be first looking at photosynthesis as a natural model of how plants, living organisms, already know how to harness the sun's energy. We've talked about the solar energy from the sun being our ultimate energy source. If you imagine plants from millions of years ago, they had just been photosynthesizing, they've been creating high energy molecules like glucose, different sugars that a bunch of consumers need. Even after these plants and other organisms have died out and they've been buried under high pressure, high temperature conditions, they end up forming our crude oil reserves, our petroleum products and whatnot. Ultimately, all the energy had come from the sun, whether it's a very instantaneous thing like plants today, or again the coal or the different anthracite, different carbon-containing compounds that have been developing over the years. So we'll have another look at solar panels. We see here on this picture, solar panels are simply a massive array of a photovoltaic cell. Again, a photovoltaic cell will take light energy, that's the photo, and ends up producing the voltage that's created in the voltaic cell. We talked about yesterday setting up these PN junctions. These have all to do with semiconductors. Silicon is our primary semiconductor that we look at. We would dope it with little amounts of either group 13 or group 15. If it's group 15, those elements here have more electrons than silicon does. Those extra electrons act as charge carriers. That would end up producing what are called N-type semiconductors. If I dope it with instead group 3 or group 13, which end up having 3 out of the 4 valence electrons that silicon has, this one has less electrons, so P-type semiconductors or doped semiconductors will have positively charged holes. Yes, you can think of them as the lack of electrons, so lacking a negative charge, but you can also consider them as positive charge actually also being moved around. We put the P-type and the N-type junctions together. We know that the holes and the electrons will naturally form a depletion layer in the middle. It'll create an electric field that doesn't let any extra holes or any extra electrons form. And once that forms there, we can set up an external circuit to run the rest of our electrical devices. So we're going to have another look at solar panels, and eventually we're going to work our way to what's called a Dssc, a dye-sensitized solar cell. And basically, as we'll look through a little bit of the details, we're going to see that the dye molecules are actually sensitive to light, just like chlorophylls and chloroplasts in living organisms are sensitive to light. The light is used to excite and create these extra electrons and extra holes. Because of that depletion layer, we can set up an external circuit and cause the electrons to travel around. So that's the direction that we're heading here. Let's just flip our way through the slides and then we'll go through some more details. So solar panels are this massive array of photovoltaic cells. Definitely it only works under high sunlight conditions. So in places that are very cloudy or whatnot, you may need to concentrate the sunlight before this can be advantageous. So solar panels, they mimic or they're analogous to how photosynthesis works in plants and different vegetation. Remember, the advantage of using solar energy, unlike nuclear, which takes nuclear, converts it to heat first, and then converts it to kinetic, and then converts. Every time we lose energy due to transformations, in this case here, this is a direct transformation between the light energy, either from the sun or some indirect source, and converting it into high energy chemical molecules like sugars, like different fuels that other consumers, even our automobiles run on, petroleum fuels, high energy products. So what we have here is the equation for photosynthesis. Okay, this one here is taking raw ingredients of CO2 and H2O. Those are really common ingredients in the earth. It absorbs the light energy, it's endothermic, and it stores that energy inside. This C6H12O6 is the glucose molecule. Glucose is the high energy molecule that consumers will end up using, burning for cellular respiration, for all of its other functions. So that's just one simple reaction. Plants will do more than this. So in other photosynthesis, it could create other sugars like sucrose and fructose. We're just going to use glucose as a nice example of it. So how do plants actually do this photosynthesis? We're going to take a look inside the plant cell. They have a specific type of organelle called the chloroplast. The chloroplast actually does look green in color because chloroplasts here, you'll notice they actually have stacks and stacks of these little intracellular organelles here. Inside these little discs here, I think they're called stoma, they actually contain the molecule chloroplast. And chloroplasts here They look green to us on the outside. Remember from our chapter 2, the reason why they look green is not because they absorb green, it's because in the visible spectrum, they absorb everything but green. So if I look at the color wheel here across from the green, they may be absorbing like a reddy, orangey kind of wavelength. That gets absorbed, that doesn't get through, and what ends up getting transmitted is the green color that we see in its place. So anything that we see color definitely absorbs some visible wavelength. It's important for you to remember that's the complement that gets reflected. So it's the chloroplast, the chlorophyll in the chloroplast that actually are responsible for absorbing this light here. We studied this a little bit here. How come chlorophyll and other molecules like it are able to absorb this light energy in the visible spectrum? Chemically speaking, it's due to these molecules having a conjugated structure. If you remember from earlier in our notes here, a conjugated structure, here's an example of a couple molecules here that have conjugated structure. If you haven't seen this yet, what are some things that all of these molecules have in common? So if you're able to see here, well, we notice that we do have double bonds and single bonds, and they're in this alternating fashion. This actually allows for conjugation. It's very similar to the pi delocalization, but in this case here, it's not necessarily delocalized, but it still has this double, single pattern. This alternating single and double allows this conjugation in structure, and it allows for us to actually absorb light. So when we actually take a look at the chlorophyll molecule, it's a horrendously large molecule. We've talked about in our notes here, this part here is called the porphyrin ring. This part here is where chlorophyll mainly has its conjugation. So if we circle all the where we have the alternating double and single bonds here, we talked about the more extensive this conjugation, the longer the conjugation network is, the higher the wavelength that's actually being absorbed. So chlorophyll is an example molecule that actually has this conjugation. It absorbs the orangey, yellowy wavelengths, and we end up seeing the green color visibly. In the conjugated structure, you know, for every one of those double bonds, those are actually pi bonds from pi electrons, or electrons in those unhybridized p orbitals. Those pi electrons, when they absorb light, they get excited to a pi star energy level. That's where the absorption takes place. That's where one of the colors gets absorbed. And they're reminding you here, as the length of the conjugation increases, as we go from having only it doesn't say here, but let's say ethene here only has one double bond, butadiene here has a double, single, double. This one here starts getting longer, maybe 5 or 6 conjugation, beta carotene, or even chlorophyll with that big ring structure. As we get longer and longer conjugation, you'll notice that there is an increase in the wavelength that actually gets absorbed. You'll notice for these smaller organic molecules, these ones only absorb in the UV region, so these ones will still be colorless to us. It's only when we get to at least, let's say, beta carotene with 11 conjugation here, that's when we start absorbing a visible color, and that's when outwardly we absorb visible and we also show a visible color as well. So the longer the conjugation, the energy that's needed for excitation decreases, so it's able to absorb a less and less energetic color, evidenced by a higher wavelength. Right, so that's chlorophyll there. We have that general increase in trend, and especially in the visible, we see the opposite color of what's being absorbed. So this is our main sort of mimic or our analogy. This is something that we can engineer in the lab so that we can mimic, even if we don't use actual chlorophyll molecule, chloroplast, in living plants. How can we mimic that function? So this one here, again, we're going to relate, it's going to be called the Dssc. It's a dye-sensitized solar cell. At the heart of it, it is a solar cell. It is a photovoltaic. It is trying to convert light energy, photo energy, into electrical energy. But what we're going to be doing is we're using a chemical dye that actually mimics the chlorophyll molecule. This dye here has to have that conjugated structure. Depending on the length of the conjugation, it's going to vary what type of energy light it absorbs. And again, if it's able to absorb this energy light, we're able to harness that light energy just like plants do with photosynthesis. We excite those electrons, we create those extra electrons in the conduction band. Electrons can't naturally go through, they have to flow through the external circuit, and that's where we can taper off the electrical energy. So here already in our equation, we have this D, which stands for the dye molecule here. The D star is actually sort of an excited form of this dye already. We're going to see the process step by step. This one here actually is a thing that gets oxidized. It ends up dropping off its electrons. We're going to see that the dye is sprayed over a titanium 4 oxide layer. They're nanoparticles to increase surface area and whatnot, but basically, once the dyes have absorbed the light energy, they pass their electrons over to the TiO2. The TiO2 ends up transferring the electrons through the external circuit back to the cathode, where we have an electrolyte that gets reduced and the cycle starts over again. So let's look through in a little bit of detail here. The dye molecules are the things that have the conjugation instead of chlorophyll that absorb light. Definitely you can engineer different dyes to absorb different wavelengths of light. It promotes those electrons into higher energy levels. So imagine starting with dye, just D. When it absorbs this light here, it becomes this D star molecule. And after this D star molecule has picked up that extra energy, it ends up getting oxidized, losing electrons, being passed over to the TiO2. So electrons are passed to these nanoparticles. Again, nanoparticles so that they have much surface area. The TiO2 will actually have an abundance of electrons. Those electrons are excited electrons that are already in the conduction band because we've engineered it in such a way that the TiO2 is not directly necessarily in contact with the I minus. It can't transfer electrons or holes very easily. The electrons, like before, are forced to go through the external circuit. So the electrons have arrived at the TiO2. They're in the conduction band of the TiO2, and they basically wrap around. Anytime we have electrons flowing in one direction, that gives us a direct current. That's where we taper off the electrical energy. That's all where the oxidation is happening. On the other side in the red here, it could be any material. We typically use the iodide and triiodide combination. This one here will perform the reduction. This one here will then regain the electrons, and that'll complete the circuit, allowing for new, fresh electrons to be absorbed by the dye, and this thing here to cycle over and over again. So that one there is a dye-sensitized solar cell. It's analogous to, in photosynthesis, we have what's called the electron transport chain. If you've done any biology, it's kind of a lot of details how the electrons follow through different cycles. In this case here, we have it a little bit more simplified. We have the oxidation happening where the TiO2 is. The electrons are forced to go through the external circuit, and then they get picked up by the iodide. Once they arrive at the cathode, we have a reduction that ends up occurring. Reduction is that gain of electrons. So triiodide gains 2 electrons, becomes 3I minus. Okay, it picks up those extra electrons and completes the circuit. Right. The I minus is typically adsorbed into an electrolyte. Again, there's a little bit of engineering to this. How do we actually create the cell here? How do we actually design the actual array itself? But at least the chemistry, how it's going to work is as we've shown here. So the oxidized dye, right? Or so the dye was excited to a dye star. It was oxidized. It's still in a high energy state. It's still got ionized, so it's now a plus charge. Part of the I minus's job in reducing it is to actually reduce those D plus molecules back to just ground state dye, and the dye is ready then to absorb extra light energy again. Important here when they start talking about what's the advantage of using Dsscs, we're going to see this more so on the next slide here, but TiO2 is it's basically a dye sprayed on top of the TiO2. The TiO2 already itself is a nanoparticle. The more surface area that we have, the more places the dye can actually absorb to, and the better chance of you being able to absorb either sunlight or redirected light from some other source. So a huge surface area that helps maximize the efficiency. The electrons travel through this wire, it powers whatever device that you want, and then the iodide, triiodide does the reduction. So the advantage of a Dssc, basically a cell that mimics photosynthesis versus just a plain old photovoltaic. This is how paper 3 tends to word questions, so make sure you can list off some of these details. We talked about TiO2 being nanoparticles, so huge surface area. That means the incident radiation can come and strike different areas of the actual particles. There's lots of surface for you to work at. The Dsscs are cheaper to manufacture than photovoltaics because all it involves is spraying chemical dye on different nanoparticular surfaces. The efficiency of photovoltaics decreases as temperature increases. Basically, in a natural like solar panel cell, it gets hot. Basically, there's increased vibrations in the structure, and it makes it a little bit harder for a regular solar panel, a p-n junction, to actually sort of react under that high temperature, whereas Dsscs are found to be less affected. And for Dsscs, because they have that higher efficiency than a photovoltaic, even if you're under a low light condition like a cloudy day or whatnot, there might still already be enough photons, doesn't need that much concentration, and basically the electrons can still work in that fashion. So We just looked at photosynthesis as a model in plant cells and then ended off with the Dsscs. Just to finish off this lesson here, we'll just flip over to our notes again. We'll have a look at some of these extra details. Remember the notes you have in that shared Google folder there. Read through some of the more details there, but hopefully that helps you with understanding what's happening here. So yesterday we left off with a little bit of the p-n junctions from earlier, how it ends up creating a depletion layer, how we basically have a natural barrier that charges can't pass over, depending on whether I have an external power source here or an external wire that's hooked up in the right direction. Basically what's going to happen is the solar energy from the light is going to create electrons. Those extra electrons in the n-type semiconductor create extra holes, those lack of electrons in the p-type semiconductor, and depending on how we hook up the circuit, we can force the electrons to go through this external pathway and taper off the electrical energy. Again, the advantage of using a solar cell here is the sun is, for us, an unlimited energy source. It shines everywhere. Obviously, some places are more sunny than other, but the sun shines everywhere on the globe. So as long as you can harness it, you have a little bit less dependence on other ways like fossil fuels or nuclear fusion. So any alternative energy can be helpful. The disadvantage here, again, sort of what was good is also bad about it here. You need that sunlight exposure. So let's say when it's nighttime, you're not going to get nearly enough incident radiation to actually run your devices. You might need to engineer some fancy storage system. It tends to have to cover large areas, and there's sort of an argument, well, what if this large area could have been used to grow crops and whatever? There's also an argument with, well, if I'm spending all these large areas for making solar panels or these Dsscs, what sort of opportunity costs am I losing for using up the land that way? So here we have a picture of a Dssc. It's pretty much the same as we had from the PowerPoint slides that we had there. Let's just walk over some of the details here. It's important for you to note that the dye behaves like the chlorophyll. It has that conjugated sp2 structure. Remind yourself that conjugated means alternating. I don't know why I didn't put my computer down. Alternating double and single bonds. Okay. Like the delocalization stuff, but not necessarily electrons can move around here. The p orbitals are ending overlapping. We're going to start over here. These ones here are TiO2 molecules. They've been sprayed over with this dye, and it's the dye that actually absorbs the incident radiation. So for example here, we're going to start off step number 1. The dye here is going to absorb the light's radiation and become dye star. These are like those pi star electrons. It's absorbed the solar radiation. The dye star, the dye coating on all these TiO2, the dye star ends up oxidizing and ends up losing electrons to that TiO2 layer. So all the electrons get dropped off in those nanoparticle sized TiO2s. They get dropped off there. We hook up an external circuit which allows electrons to flow from the one electrode to the other electrode. Remember, this is where we taper off any electrical energy, run our electrical devices. That's where the oxidation occurs, so that's more so the anode. On the other side with the cathode, we have to have something that gets reduced. Again, for us, we're going to use the example of I3 minus. I3 minus gets reduced back into 3I minus. You can balance it for yourself later on, and basically that gains the electrons back and completes the circuit. So we see here the X here, this one might represent I3 minus. This is adsorbed into the electrolyte surface. This was that other surface, the I3 minus. It's sort of in contact with the TiO2, but we have set it up in such a way that electrons can't just naturally cross over this barrier. We want to force the electrons around the rest of the way. Right? So the dye star, so the I3 minus ends up gaining some number of electrons and becomes I minus. That's step number 3, giving you an overall, here's your net equation. It's like taking the dye star, the dye plus, the oxidized form, and actually reducing it back into the regular dye so we can start again. Okay. Sorry, I guess it's better to say this is step number 4 because that just fleshes out a little bit. The dye star actually picks up, reacts with the I minus, which has gained the electrons, and actually regenerates this dye non-starred form. So that there is a Dssc. Hopefully you see some of the analogies with how photosynthesis works out. This is their favorite question of theirs. Give me some advantages and disadvantages versus Dsscs versus regular photovoltaics. We've already talked about a lot of this here. One that they always like talking about is the large surface area for the nanoscale TiO2. We can typically manufacture it using very low-cost materials. It's not as mechanically dependent. Works in low light conditions like cloudy skies. One of the disadvantages, however, especially when we start looking at sort of what state of matter these electrolytes are in, it's said if it's really, really low temperature and the liquid electrolyte actually freezes, it can cause physical damage. If we're too high temperature, earlier we said DSSCs aren't as sensitive to temperature, but if it does get really, really hot, we end up getting some sealing problems. As they've tried to work around this here, they realize instead of using I3 minus iodide or even iodine as a combination here, they found that actually using a thin film of the cesium compound actually it's less mechanically dependent, and that sort of addresses this disadvantage. And here, one last one that wasn't super obvious was the dye molecules tend to have a very poor red absorption as compared to a regular silicon. So the actual wavelength that gets absorbed may be very specific to the individual dye, whereas silicon can absorb a much larger range and actually utilize more of the sun's energy. The dye may only have access to a very narrow region. So that's it for our solar panel section. So if you have any questions, just feel free to let me know, and then we'll talk more in detail next week. Thanks, guys. Take care.